We're going to take a look at the difference between the asynchronous reset on the 74HC161 and the synchronous reset on the 74HC163. As you'll remember, that's the only difference between these two counters. They're both binary synchronous counters. The counters themselves are synchronous. They use the same clock on all the flip-flops. The difference is how they reset. One, the 74HC161, resets whenever the clear bar is asserted, and the 74-163 resets or clears to 0, 0, 0, 0 when clear is asserted and there's a rising edge of the clock. This is our test board, and let's go take a look at what the circuitry looks like. Here is a 7416X, where X can be either a 1 or a 3. It has power. Both enables are connected to 5 volts, so it always counts when there's a clock edge. The 4 load inputs are connected to 0, and the load input itself is connected to 5 volts, so that's not used. So we have our 4 outputs, QA through QD. We're only going to be looking at the 2 lower order bits, QA and QB. And the QA and QB are connected to a NAND gate, whose output is connected to the clear bar input. And the one thing that's a little different about this, we have a NAND gate, which is connected to QA and QB, but the pin that's connected to QA can alternately be connected to 5 volts with a switch. So when it's connected to QA and QB, the output of the NAND gate will go low when QA and QB are both high. That's a count of 3. 0, 0, 0, 1, 1, 0, 1, 1. So after 4 clock cycles, that output would go low. Alternately, if we connect the NAND input on pin 4 that's normally connected to QA to 5 volts, the 74HC00 effectively becomes an inverter, and it inverts QB. So our count is going to be 0, 0, 0, 1, 1, 0, and on a count of 2, 1, 0, the output of the NAND gate will go low, asserting clear. And depending on whether it's a 161 or 163, the counter will either clear immediately or it will clear on the next rising edge of the clock. So let's start out looking at this circuit with a 74HC163 in it, and with the switch set so that pin 4 of the NAND gate is connected to plus 5 volts. That is, the output of the NAND gate goes low when we get to a count of 2. So we're going to move on over to our oscilloscope. Okay, we're putting a clock of about 100 hertz, you can see that down here, into the 74HC163. Here's our clock signal on the top line. Just below it is QA, and below it is QB. And if you look, what you see is we start out with a count of 0, 0, we go to a count of 0, 1, we go to a count of 1, 0, and then we go to a count of 0, 0. Now, why is that? Well, remember that we have QB inverted and applied to the clear input. So when QB is low for a count of 0, 0 and a count of 0, 1, clear is high. When we go to a count of 1, 0, clear goes low, and on the next rising edge of the clock, we reset the counter back to 0, 0. And if you look at this, the output that we see either on any 3 of these is the clock divided by 3. Let's go ahead and add a measurement which shows the frequency of the output of this circuit, which in this case could be either Q0, Q1, or the clear input. Okay, so our frequency on channel 1, our clock, is 104 hertz, and our frequency on channel 4, which is in this case the clear output, is about 35 hertz. This is a divide by 3. Now, the question is, what happens if I replace the 74HC163 with a 74HC161? Okay, so we've now replaced the part with an asynchronous clear, and notice that we count 0, 0, 0, 1 back to 0, 0. That doesn't make any sense. QB seems to always be low, and its inversion on channel 4 is always high. What is going on here? Well, what's happening is we actually are counting 0, 0, 0, 1, 1, 0, But when we go to 1, 0, we immediately clear the counter because it's an asynchronous clear and go back to 0, 0. And that count to 1, 0 is happening so quickly that we can't even see it. So what we're going to need to do is zoom in here. We have our count of 0, 1, and then we go to a count of 1, 0 for a very short time. This is 20 nanoseconds per division, and you can see we go to a count of 1, 0 for approximately 20 nanoseconds. We invert that count, the most significant bit, which is to say QB. We get about a 20 nanosecond low pulse going into clear, and since it's an asynchronous clear, that's enough to cause both outputs to go to 0. When QB goes to 0, clear goes back to 1. So we actually are counting 0, 0, 0, 1, 1, 0, but it happens for such a short time that you can't see it unless you zoom in on it, which is one of the problems with asynchronous clears, is that it's very hard to tell what's going on. Another problem you've got is that you only have this 20 nanosecond pulse, and it may or may not be fast enough to trigger whatever you're looking at. If we wanted this to be a divide by 3, what could we do? Well, looking at the schematic, we see that instead of resetting when QB goes to 1, we can reset when both QA and QB go to 1, which is a count of 3. If we do that, and I can do that very easily by switching the NAND gate, now we've got an input frequency of 100 hertz and an output frequency of about 34 hertz. We now have a divide by 3. We still have the problem that we are counting 0, 0, 0, 1, 1, 0, and then for a very short time here we are counting 1, 1. When we do that, we're getting a reset pulse, and once again we need to zoom in to see that, way in. And sure enough, when we zoom in to 20 nanoseconds per division, we see we've got the count of 1, 0, and then we go to 1, 1 for 20 nanoseconds. We NAND that together to get a low pulse, which causes the counter to clear, and we get an output 0, 0 in the counter. Once again, this is a very poor way to divide by n counters. By the way, what happens if we were to use a 163 and decode 1, 1 to reset the counter? Well, I can just go back to my 74 163, and what we have now is we have a divide by 4. We're counting, let's move over so we can start at 0, 0. So our counter starts out 0, 0, 0, 1, 1, 0, and then it goes to 1, 1. We NAND that together, go low, but we don't reset until the next rising clock pulse back to 0, 0. So counting 0, 0, 0, 1, 1, 0, 1, 1, back to 0, 0. That's a divide by 4, not a divide by 3. How do we fix that? We go back to just looking at QB, not looking for a 1, 1, but looking for a count of 2, and we're back to a divide by 3. So this is certainly much easier to debug than having to zoom in on a 20 nanosecond pulse, and that's why we always want to use a synchronous reset rather than an asynchronous reset for doing divide by counters. Okay, it's time for me to fess up. I actually have been cheating a little bit. Let's take a look at this actual demo. I am not switching between a 74HC161 and a 163, although I claimed I was. My actual demo has a switch that lets me apply the output of the NAND gate to either the clear input or the load input, and I've got some pull-up resistors, so whichever switch position is not used, that input is high or not asserted. And I'm only using a 74HC161. Why am I doing that? Well, we know that load is always synchronous, and clear can be either synchronous or asynchronous depending on if it's a 161 or 163. If I have all the load inputs set to 0, then load effectively becomes a synchronous clear, and clear is an asynchronous clear since I have a 161. So I have a switch that lets me switch between the apparent behavior of a 161 and 163, even though I'm just using a 161 counter. I hope you'll forgive me that little cheat, otherwise I would have to stop the video, pull out the 161 and plug in the 163. This allows me to demonstrate both synchronous and asynchronous clear with just a 74HC161.